The first talk is this long title from this extremely large consortium of European institutions, and the presenter is Gauthier Lefrey from the Universiteit Libre de Brussel, who is just about ready.
Okay, I will present this paper in name of a lot of people that are actually working in MPEG-FTV, so that's the MPEG-free viewpoint TV, thank you, activity, and I'm actually the co-chair of MPEG-FTV, and Tanimoto-san, the last author, is the chair of MPEG-FTV. So you probably know MPEG for everything about digital TV. It's a single view codec, but MPEG has also developed multiple view codecs that now basically are called the 3D HEVC. So it stands for 3D high efficiency video coding, which transmits all the views you want, so not only two, you can have tens or hundreds of views. And it's also transmitting depth maps. And based on these views and the depth maps, you can do a nice view interpolation. So it's very useful for everything that is related to light field displays, where basically you project a lot of views, hundreds of views in all directions. And of course, these views have to be captured from somewhere. So you take a number of cameras, hundreds of cameras, you do the compression, and then you transmit that to the light field display to present all the views. This works fine when you have linear camera arrays and when the cameras are very, very close to each other. In other conditions, when you have a general camera arrangement, or even if the distance between the cameras is too big, it's not so sure that 3D HEVC works well. And that's why MPEG has issued a call to find new technology that would solve that problem. So for these challenges of nonlinear camera arrays and large inter-camera distances, we are looking for other technology or improvements of 3D HEVC. That's why I'm using here the 3D HEVC++ terminology. And actually, I will give you here in this presentation only a preview, sneak preview of the technology that has been developed, because it will be evaluated in San Diego starting from this Saturday. So I can only give you a general summary. So what we have done is basically we have given people a number of test sequences with 7 cameras, and some test sequences with 80 camera feeds. And then, oops, sorry. We basically have compressed these sequences with 3D HEVC. And here you see basically the bit rates that we have with the current 3D HEVC settings. And then we asked the people to develop technology that would give the same quality at lower bit rate. And actually, I will not go into the details here in this presentation, but some people have 10, 20, 30% bit rate gains by providing some optimizations of 3D HEVC. So as I said before, it will be evaluated during the San Diego meeting, MPEG meeting, well, starting this Saturday. So the main trick that most of these people have used is basically to reduce the number of cameras. So if you have 80 cameras, instead of transmitting all these views, you just skip some cameras and you re-interpolate, you recalculate basically the missing views. Whatever you do, it will always reduce the bit rate. So the bit rate is always a linear function of the number of cameras. So if you reduce the number of cameras that you transmit, you will reduce the bit rate. But it's very important to have good technology that does the interpolation right between existing camera views, which is a challenge. And actually, that works well when you have a lot of cameras close by, close to each other, but it doesn't work well when the cameras are far from each other, and that I will directly show you. But let me first tell you how it works, that interpolation. Basically, it's based on depth image-based rendering. So what you do is you have a scene, let's say with flowers and some objects and then clouds in the background. when you look at this scene from different viewpoints, a left camera view and a right camera view, that's what you see. Actually, the clouds being very far away, they basically do not move from one view to another. But the flower being very close by, there is a disparity when you go from the left view to the right view. It's like putting your finger in front of your eyes. When you switch from one eye to the other, you see your finger moving. When you put your finger very far away, it's not moving. So that's called disparity. So the flower in one view is somewhere at the left of the image. In another view, it's at the right. And the disparity is the displacement that you have. And if you want to create an intermediate view, halfway between these two views, you basically just move the flower half the disparity, and that will be the view that you see halfway. The problem, of course, is that the flower that was here at the left is now moved in the middle, so there is a hole here that you have to fill in, and so there are many techniques that exist. I will not go into the details for that, but this is the main principle of doing a view interpolation in 3D HEVC. And as I said before, it works perfectly fine when you have cameras very close to each other, but it doesn't work so fine when the cameras are quite far away from each other. So here we have transmitted 7 camera views, and suppose that you are just moving in front of the light field display from left to right all around. So if you do nothing at all, you get what you see here at the left side. You just switch from one view to another in a very discontinuous way. If you use that view interpolation, you have a more fluent view, but you see here all the flowers, there's something wrong, because there are a lot of occlusions that's very difficult to solve. So this is a very challenging sequence. But you see the bunny himself, it's quite okay. The tree are okay, but everything around the flowers is really a challenge. So this software is what is called view synthesis reference software. That's the anchor that we are using, and we try to find technology that performs better than this. Actually, a close-by view gives you this. Again, this is a view interpolation from camera views that are far away from each other. That's why it's not working well. That's typically the result that you get. And you see these kind of artifacts all around. But it's even worse when you do compression. You get really a very messy thing. And actually that compression is transforming this disparity, this depth map, so everything in white is close by, everything that's dark is far away. It's coding that, but it's always lossy coding, so you get some artifacts left and right, and you see here blocking artifacts, and that has an influence on the view synthesis, which makes the view synthesis even worse. So we have to be very careful about depth estimation in 3D HEVC, especially when you have a large baseline, so cameras that are far away from each other. Some people have improved what I showed you before. Here, for instance, that's, again, that view interpolation. It's still messy, but it's better. There are some things here that pop up that you don't have at the left side. So there's still room for improvement. So this is an example where basically from the 80 views that you would transmit to the light field display, you only transmit 7, and you calculate all the others. Doesn't seem to work well, but here on this sequence, it works quite well. So here we transmit 13 views, and all the other views are basically interpolated, and it gives quite good results. So you can imagine how much bitrate you gain by doing that. You basically reduce the bitrate with a high factor, and you don't see the interpolated view. So you have to imagine that 20% of these images are transmitted, and the 80 other % are basically calculated. Actually, if you take a close look, you will see artifacts. You see here artifacts around the butterfly. And if you take the quality as a function of the view position, so you have 80 view positions here. Well, if you just transmit the 80 views with compression with 3D HEVC, you would have the green line. If you transmit only 13 views, and you do the view interpolation for all the others, you get basically the red line. So the peaks correspond to basically views that you transmit, and the valleys correspond to views that you have calculated. And you see here that you get a reduction of quality of 4 dB, which is huge, I know. So a lot of people say if you're above half a dB, you have a big decrease of quality, but you don't see that. So on a light field display, it might be okay to lose these 4 dB. And that's also something that we will evaluate in the coming MPEG meeting. This is a close view of the artifacts. So in the case of the bunny that I showed you before, you have more or less the same phenomenon. You have the views that you transmit and all the intermediate views that have a much worse quality. Here you lose 10 dB, which is really too big, unacceptable. Up to now, I've presented you basically sequences that are 3D graphics sequences. So you have the views, 7 or 80 views, and you have also a perfect depth map or perfect disparity map. So there are no artifacts on this depth map except if you compress it and transmit it. But with natural content, it's even worse because you have to estimate the depth map. So the depth map is not perfect. And so you can imagine that the view synthesis is then very bad. But actually, if you look to this sequence, so we start from 7 input cameras all around the scene, and we interpolate hundreds of views in between the two extremes. And that's what you get. So indeed, there are still errors around the silhouettes here, but that's because there are a lot of occlusions. For instance, the chair here is only visible from 2 cameras out of the 7, so it's very difficult to do the interpolation. But you have to look to these blocks in the middle, where there are a lot of occlusions, and still, with some improved technology, you get quite good results. There's sometimes a little bit flickering all around, but the results are quite good. So you can really do a free navigation, a fly through the scene, starting from 7 camera inputs and just interpolating between these 7 views. And by the way, this proposal also has a bitrate gain of 10% compared to 3D HEVC. This is another example. Again, you have 7 input cameras, you estimate the depth map, and then you do the interpolation, and here you have a fly-through. So you have to imagine none of the cameras are moving. You really have only a virtual camera that is calculating a viewpoint from the 7 input views. And that's what you get. So here you see the fly-through. And actually, in everything that I explained so far, the depth map was estimated at the sender side, compressed, transmitted, and then the depth map was used together with the views to do the interpolation. But if you don't have to transmit the depth map, you can gain quite a lot of bitrate. So this is an example where the same people have basically dropped everything that has to do with depth, and they have estimated the depth at the decoder. So just from the decoded views. So it's again 7 input cameras, and then they compress the 7 views. They estimate depth, and then they do the view interpolation, and this is the result that you get. This is the same sequence, but with a fly through the scene while the people are moving. So I challenge you to find artifacts. There are artifacts, but you really have to look very carefully to find them. And you see at the right, at the left and the right borders, you see this flipping effect. That's because the overlapping over the 7 camera views is not complete, so you have these clipping effects. But in the middle, everything works quite fine. So actually, we might say that with this technology, that again still has to be evaluated from Saturday on, We are closer to what we would call the cinematic virtual reality. So that's basically a free navigation from, let's say, a scene surrounded by some cameras, and you just do an interpolation between the different camera views to have a fly-through, like in the Matrix. Huh? But the difference is that here we do not have to use hundreds of cameras. We only have to use 7 cameras. It's still not perfect, I agree. But we can basically reduce the number of cameras that you have here, and these are hundreds of cameras, to dozens of them, and have an acceptable bit rate to transmit all the information. Actually, all these things are further explored in a lot of standardization committees. So you have MPEG-FTV, Free Viewpoint TV, that is looking to these things, but you also have in MPEG a light field group, because basically multi-camera systems, that corresponds to light fields. Whether you have the cameras all around or the cameras basically packed together into a box doesn't make much a difference. So there's also a group that is looking to these light fields. And in my opinion, there are a lot of commonalities between these two groups, but you also have JPEG standardization committee that is looking to planoptic imaging, called JPEG Plano. So a lot of people are looking to this kind of free navigation stuff. So I think it's really the moment to be active in that field. Today, you find already on the market a lot of virtual reality 360-degree panoramic virtual reality products, where basically you have a kind of cylinder where you have a panoramic view, and when you turn around your head, you just take a portion of that cylinder. That works fine for everything that is far away. But if you have close-by objects, that doesn't work fine anymore. So with close-by objects, when you move a little bit left or right, and that's something that you naturally do, you have perspective changes that you have to correct. And that is possible with this free navigation technology. That is not possible today with the 360-degree video. And here you have some products, let's say, that go in that direction. There is Nozon that is using light field technology for being able to do this cinematic virtual reality. And 8i is using point cloud technology. All these things are quite similar to each other. So to conclude, basically there is already a 3D HEVC codec that exists that has been standardized last year. That works perfectly fine when you have a multi-camera system where all the cameras are linearly arranged and very close to each other. But we are now evaluating new technology, actually improvements of 3D HEVC for non-linear camera arrangements where the cameras are very far from each other. And that will be, as I said before, evaluated in San Diego starting from this Saturday. And it addresses basically the super-multiView light field displays and free navigation in cinematic virtual reality. So this exploration is still ongoing, so we all invite you to participate. Please join us, whether it's MPEG or JPEG, doesn't make a difference. I think it's the moment to really join and to do some progress in this field. Thank you.